So I have done a few of these live streams now, and I cannot tell exactly when it begins. I think I'm live at the moment. Hopefully everybody out there can see and hear me. So today in the live stream, we're going to be doing GCSE between now and about 8 o'clock. So about half an hour of GCSE focused stuff aimed at AQA paper 2, which is, I guess, most people watching this. And then from 8 o'clock onwards, we're going to be doing the A-level part of the stream. It does say down here on this side. And I'm going to be going through some questions from OCR papers because I can not show stuff from AQA because of copyright restrictions. Which is why for the GCSE part of the stream, I'm going to be using my own questions which I've written. You can download these. I put a link in it, but it's basically physicsonline.shop. And basically you can buy stuff there and actually have a look at that and give yourself access to many, many more questions with not only a full kind of mark scheme, but also work solutions and so on. So hi, Erin, hope you are doing well. For this one, I thought I'd do a slightly different thing. I've got basically some of my work solutions here, just to kind of show you what you might find if you were to maybe download this paper yourself. Hello, Bilal. Hello, Adono, Muffy. Hello, everybody. Hope you're doing well. So the reason I can't show AQA questions is because it's copyright material, and it's really a lot of the images are copyrighted. I think AQA only have the license for those images for a certain amount of time, maybe 5 years. And basically AQA, or not the science team are brilliant and they really want to kind of help students like you. It's just like the kind of legal people higher up because it's a massive company. So yeah, that's the only reason I can't share it. However, I've written these questions, I've formatted the paper, I've actually drawn this diagram. So this here is my own work and work of other teachers who've helped me. Heads, you are the biggest fan. Definitely are tonight. Thank you so much for the donation. I do appreciate that. And of course, if anybody out there does have access to their parents' credit cards, you can do like super chats. I think you can do donations in the stream as it's live. So obviously all of that stuff is really appreciated. So I'm just going to put on a bit more light just behind me. But Heads, thank you so much. And especially for you, I really hope that your exam goes the way it should be. So, first of all, what do we mean by a wave? So, a wave is a disturbance that transfers energy without the transfer of matter. Okay, so this is what we call a progressive wave. And basically, as the wave radiates away from something, it's going to transfer energy, maybe from one store to another. So, think about a light or a sound wave. That's a transfer of energy, but it doesn't transfer any matter. So, when you hear a sound wave, for example, you basically hear the sound, but it's not like the air particles, maybe from the loudspeaker, have actually travelled all the way to your ear. Okay, so we don't transfer matter, we only transfer energy, and that's the kind of thing that you're going to get there for your 2 marks. Yeah, you did AS level, pretty sure you got A and everything. Heads, that is awesome. I would say that if you're doing well at AS level, then that gives you basically massive confidence that you're on the right track. And if you just do the same that you're doing this year, the same way of working, you're going to be absolutely fine and pretty much almost guaranteed that A at the end of year 13. So Heads, awesome work so far. Okay, the next one is simple stuff. And this kind of comes up all the time. I suspect, like I did with my prediction for paper 1 for GCSE, that there might be a question about series and parallel and where the amplitude would want me to go. You will get a question maybe to label the wavelength. Now it could be from a peak to a peak, it could be from the trough to a trough, or indeed it could be from one point on a wave to the subsequent point on the adjacent wave. Okay, so it could be any distance, and we use the letter lambda, which is a Greek letter, lambda, and that represents the wavelength of that wave. And of course, the amplitude is from the mean position or its rest position to the maximum displacement. So it's not from the very top to the very bottom, it's just from the line up to the very top. Do you reckon, so that Prem, Go Hill, again, it's nice to see the same people in the chat all the time. Do I reckon you and your mate could learn all of AS physics after GCSEs? Yes, I reckon you could, but I don't reckon you need to. Actually, for everybody watching, oh, I I've taken the book away. I do have some books called The Daily Workout, and these cover a lot more kind of A-level physics stuff. But the first book, book 1, and it's basically books 1, 2 and 3 cover all of AS level. So you can basically buy my books, work through them, and I could explain everything to you. But if you buy book 1, there are questions to do from the start of July all the way through August into September, and that will really help you get a head start. So if anybody out there is watching this stream and is considering A-level physics, then buy book 1 of the Daily Workout. You can find links to it on Amazon. And of course, also, I apologise at the moment. Hello, the birds. There's some boy racers in the car park just outside my office. It's a lovely sunny evening. It's a big open car park, so you might hear some noise. I don't know how much the microphone picks that up, but yeah, I think they've gone in a second. Right, so that's the wavelength here, and that's the amplitude. Now, the next question is about something that you should know what it is. This is an oscilloscope. And here the student uses a microphone connected to an oscilloscope to investigate a sound wave travelling through the air. So you don't need to know too much about the setup, but what we can do is there are 2 dials. Basically, you've got the Y gain, which affects the Y-axis, which is often measured in volts, and that gives the size of the voltage of that electrical signal that it receives. And on the X-axis, we call this the time base. So effectively, what we have here is a graph where on the X-axis you have time. Okay, so that is an oscilloscope, and we're going to come back to that in a bit. Right, 1.3, define the frequency of a wave. So this one here is just easy marks, and the way that I've seen AQA define the frequency of a wave in their specification is the number of waves passing a point each second. If you learn that, you've got a guaranteed 1 mark. So the frequency of a wave is the number of waves passing a point each second, or it could be the number of complete oscillations per second, or the number of oscillations per second. But this here is basically the AQA wording. So describe how the frequency of a sound wave can be calculated from the trace on the oscilloscope. Now, on the oscilloscope, you cannot measure the frequency directly. Instead, what we can measure is the time period. Okay, now because on the X-axis we have time, that means if we look at the length of one cycle, it could be from the midpoint to the midpoint, from the top here to the top there, or the bottom to the bottom, one wave cycle has a time period of capital T. And that's basically for one cycle of that wave. Okay, and of course, if you know the time period, we can relate that to the frequency, because the frequency is equal to 1 over the time period, or we could say that the time period is equal to 1 over frequency. Now, from the graph here, what you can do is you can measure, using the scale here, the time, often a very, very small time, perhaps like it might be measured in milliseconds, and then heads says you find the reciprocal. So whatever the time period is, you do 1 over that number, 1 over t, and that tells you the frequency. Okay, and yeah, so you multiply the time base by the number of squares for a full cycle. So for example, the time base might have a reading of maybe 0.1 of a second. Okay, you can see here that we've got 1, 2, 3, 4, 5, 6 squares. So the time for that would be 6 times 0.1, which is 0.6 of a second. So here, all you need to do is multiply the number on the time base by the number of squares to get the total time, 0.6, and then the frequency would be equal to 1 over 0.6, which would be, like 1.7 or something. Okay, so measure the time period for one complete wave cycle using the scale to convert to time in seconds. Again, sometimes, and this is kind of like the kind of top tip, is they often give you time in milliseconds, and a milli is times 10 to the minus 3. And then to calculate the frequency from f equals 1 over t, and of course frequency is measured in the unit of hertz. Okay, if the student were to investigate a wave that had the same period as the sound wave, but travelled at 450 meters per second, state how you would expect the wavelength to compare. So for this one, we don't need to explain it, but basically it says here that they're looking at a sound wave travelling through the air. Now we know the speed of a wave in air is approximately 330 or 300 or 340, something around that region, meters per second. Okay, we also know that the wave speed is equal to the frequency multiplied by the wavelength. Okay, now if the wave had the same period, that means if t is constant, then it must also have the same value of frequency. Okay, and what we can see here is we can see that if it had the same value of frequency, then the wave speed is going to be proportional to the wavelength. Okay, so the value of f is going to be a constant, and that means the speed of the wave is going to be proportional to the wavelength. Now, when you've got a value of about 330 meters per second, this has got a certain value of wavelength. If we increase the value of v, so this is now travelling at 450 meters per second, then because the value of v goes up, the value of the wavelength increases as well. So you can state here that the wavelength would be longer. Now this kind of bit here, the kind of explanation of physics you don't need to know about or don't need to actually describe, but you need to understand it in order to answer this. However, this question here is very much, it's either going to get bigger, stay the same, or get smaller. And often things don't stay the same. So really you've got a 50% chance if you don't know anything else. It's either going to get bigger or smaller. Okay, right, yes, some questions that people are asking. The time period always has to be measured in seconds. So convert from milliseconds into seconds, and that will give you your frequency in hertz. And of course, yeah, for anybody out there who is maybe thinking about A-level, I've tried to make these questions like really suitable for the people like you watching this, the people who are aiming for the really, really high grades, which I'm sure you're all aiming for. Actually, if you'd like to, if you want to let me know in the chat what you're hoping for, what's your, not so much your predicted grade, but what is it that you're aiming to get at the end of GCSEs. I suspect that most people watching this today are kind of aiming for like a 7, 8 or a 9, and these questions here are at the top end of GCSE, and that will help you prepare for A-level as well. Right, we then have a question saying, waves can be observed in the classroom using a device called a ripple tank. So some of you might have seen the really kind of small tabletop ones. This is your old school kind of way where we basically have a big tray of water. Often you shine a light from above and then you kind of project that image onto the table, or if your teachers are professionals and they know what they're doing, you project upwards and then you're going to get a massive wave on the ceiling. And you basically have a motor with an off-center mass and a dibber that goes up and down, and that sends a wave along there. So the question says, with the motor set to a frequency of 75 Hertz, and I've just highlighted that number, the student measures the speed of the waves as 4.5. So we know the frequency and we know the wavelength. Of course, we also know the distance from the dipper, or dibber, to the end of the tank is 30 centimetres. How many waves would be visible in the ripple tank? So basically, if we know the total length, L, we want to know the value of the wavelength, which is the wave, the distance that one wave takes up, and that means the number of waves is going to be equal to the total length divided by the wavelength. Okay, so this one here, that's not an equation you're given, it's just kind of almost like common sense. If you know the length of a wave and the total length, how many waves are there? So we can say that the wave speed equals the frequency times the wavelength, and that means the wavelength is going to be equal to the speed of the wave over the frequency, which is 4.5 meters per second divided by 75 hertz, which is 0.060 meters. Okay, so that is the wavelength. Now, the number of waves is going to be the total length, which is 0.30 meters, divided by the wavelength, which is 0.060 meters. So keeping meters as kind of common SI unit, and this gives a number of 5. So the number of waves is equal to 5. So that's how many complete waves would be visible, and that's why I've just given it as 5, because it's like an integer. It's just the number of complete waves. So that question there, I think hopefully was all right. How are people getting on? Does anybody have any questions at the moment related to the the topic of waves, or any kind of simple things that you're maybe not sure about that I can answer. If so, there's not many people watching tonight. I know a lot of people are kind of pretty tired from doing maths. You had maths paper 2 today. I hope that went really well for you. I know that the foundation paper was treated or found to be quite easy and relatively straightforward. I know a lot of you have history tomorrow afternoon, and I suspect there's probably some other exams in the morning, but hopefully all of you are doing okay. Right, the next question is kind of more interesting, and this is very much a triple science topic only. So if you are doing trilogy or maybe combined science, this might not even come up, and actually this is one of the most interesting areas of GCSE. So describe how the Big Bang describes the beginning of the universe. So basically, the Big Bang started from an infinitely small and dense point. Now effectively, because it's infinitely small, that means, you know, the diameter of that Big Bang is equal to 0. Okay, it's like it's got no dimensions. It's not, you know, 0.00001 millimeters. It's just got no dimensions. It's smaller than we could possibly measure. And of course, all of the mass, or all of the energy which has been transferred to the mass, is contained within this, and therefore, you know, the mass over volume, because the volume is 0, we're going to have an infinitely dense point as well. And then for some reason that I can still not really get my head around, it then started rapidly expanding, and that created all of space and all of time. So before the Big Bang, there wasn't time. So there wasn't a before, it just started time, because before that time didn't exist, which again doesn't really make any sense to my logical brain. But basically from the Big Bang, stuff rapidly expanded, it created all of space, all of time, and all the matter that we've got around us. Okay, the next bit is a kind of bit of history, because although we often talk about Hubble's law and there are certain scientists that we know about, they're not always the people who did all of the work themselves. And often there were, you know, competing people working in different countries, people kind of adding little bits to the theory, but then maybe one person had it named after them. So Hubble did some work. The idea was first proposed by Georges Lemaître. I think it's my French. And basically, the properties of light from distant galaxies that provides evidence for the expanding universe is that light is redshifted. And that's because it's stretched by the expanding universe. So imagine you had some light, which was maybe initially blue, and this was maybe the wave that's emitted from something. Okay, now if that thing and the observer are moving relative to each other, then what's going to happen is that we're going to see that that light is stretched. And as it's stretched, it goes towards, if it's visible light, then it's going to be stretched towards the visible part of the spectrum. So what you should remember is that, you know, you've got radio, micro, infrared, visible, ultraviolet, X-rays and gamma rays. Okay, and in the visible part of the spectrum, we have Roy-Gabiv going from the red to the violet. Okay, so if we think about the wavelengths, the violet light has a short wavelength and the red light has a longer wavelength. And as the light is stretched, it's basically going in this direction, so we have the redshift of light. And we see this when we look at the light from distant galaxies, and basically the further things are away, the more that light is stretched out. And this is because not so much that the universe, that the galaxies are moving through the universe, it's just that the universe is getting bigger, and that means everything's moving away from everything else. Okay, right, so some good questions here. Mejraf, a lot of people are posting walkthrough videos all the time, they do. And that's and I appreciate that there's lots of stuff that is on TikTok now that shouldn't really be shown. I mean, for example, I've got copies of the papers. I've got the AQA papers that were sat this year. I've got the OCR A-level ones. I've seen the AQA A-level ones. Teachers might get them later the same day, or they might be given them maybe after 24 hours, depending on the school's policy. So your teachers will see the paper, so they can have a look at it and go, yes, this makes sense. I'm glad we taught that, or maybe we need to do this better for next year. But teachers shouldn't be sharing that in the public domain. So the 2023-2024 papers, definitely the 2024 papers, shouldn't be released because they're going to be used for mock exams in the future. Now the thing is, if I show copyright material from AQA, they can basically easily do a copyright strike on YouTube, and that can get my channel taken down, which is bad. Okay, so yeah, that's why I'm not showing AQA stuff. Sketch a graph showing how the relationship between the distance to a galaxy and how fast it is moving away from the Earth. So this one here, you could have the velocity and the distance on either axis. It doesn't really matter. By convention, we tend to look at the distance away from the Earth and what we call the recessional velocity, because that's how fast it's receding. And what we see here is that the speed of recession of that galaxy is going to be proportional to the distance away from the Earth. So things which are close by are moving relatively slowly away from us. The further things are away from us, the quicker they're moving away from us. And that's because everything is expanding away from everything else. Yeah, somebody hates astrophysics. I like it. When you do it in year 13, I think it is a nice one. Okay, now the last question is something which I think is the last bit mentioned in the specification for AQA. And it's about dark matter and dark energy. So the steady state theory says, so the steady state theory about the universe before the Big Bang was widely accepted. Now we know that observations of supernova suggest that the expansion of the universe is accelerating. So if you look at a supernova, you can basically work out exactly how bright it should be. And then if you know how bright it should be and how bright it actually appears, we can work out the distance to really, really far away galaxies. And basically what it says is that the universe isn't just expanding, but the rate of expansion is increasing. So what are dark matter and dark energy? So the two things, although they have the word dark in front of them, they are completely different. The word dark, basically in physics, just means it's unknown, and we don't know exactly what it is. So we don't know what dark matter is, we don't know what dark energy is. So dark matter has mass, and basically we can see the effect that this dark matter has on other objects, although we can't see it directly. So there are things where you've basically got images of galaxies colliding and moving through each other, and they behave because, you know, gravity is the force that kind of causes these things to move around each other. Basically, we look at the number of stars, and then we do a prediction about what should happen. We then see what happens, but there's not enough mass contained within the stars that we can see that would account for the behaviour of these things. So there must be stuff in space that has mass, but it's not giving out light, and we don't know what that is. Of course, dark energy is something different. This is energy that's actually causing the accelerated expansion of the universe. But the thing is, we don't know what they are at the moment, and it's people like you who have to kind of solve this problem and actually work out what is providing this mass, what's kind of causing the accelerated expansion, and actually work out what these are. Okay, yeah, so this one over here is the end of the question we're doing tonight. I'm just going to read some of the questions. Mazraf, atomic structure and forces are the best and most interesting at GCSE. Yeah, I think motion is the best part of physics. I reckon even amongst the physics community, and I used to work with a teacher who he did a physics degree and he hated astrophysics, whereas I did engineering at university and I didn't do any astrophysics, but I really quite liked teaching about it. I liked learning about the kind of particle physics to a certain extent, but a lot of my degree at uni was like material science, looking at forces, looking at the structure of metals, and I really liked that. So you know, even people who might have very different degrees, or even people who've done physics, might love one bit of physics more than the other, and I think that's absolutely fine. I did say that the thing that I didn't like was electricity. I've learned to enjoy it now a bit more, but for me, I'd rather be doing SUVAC questions, equations of motion, looking at moments, looking at material properties, rather than doing stuff about electricity. Okay, does university level quantum confuse me? Yes, it does, because even the stuff it's like anything, when you look into a subject in more detail, you know, I understand it at A level. I know there's like, you know, quarks inside the protons and neutrons, but then when you start to learn a bit more, you realise that there are like virtual quarks that come in and out of existence inside the nucleus, and it's like, that just kind of blows my mind. Oh yeah, so I reckon for everybody, there's certain bits that everybody likes or people really like and other bits that people don't like. So again, in the chat, if you want to put what you really hate and what you really love, everybody's got their own particular interest. Yeah, there's like virtual quarks. It's difficult, but it's like interesting, but it's also like it doesn't make sense, because I suppose that's why I did engineering at university rather than physics, because I kind of liked, you know, bits of metal and stuff that you can see. Okay, right, we've got a couple of minutes. We've got 5 minutes or so until we start the A-level stream. So in that time, let me just put this over here. We're going to do a bit more space Lego if people want to do that. Backup says, A-level geezer here, you hate electricity, don't mind turning points. Yeah, I think actually turning points, which is one of the AQA options at A-level, is really interesting. There's a lot of history there, and there's a lot of kind of history of how things evolved, okay? Heads says you that despise Astro, don't like electricity, but revise the hell out of electricity so you understand it. Yeah, and I think that's what you need to do. Sometimes if it's the area that you don't like, you need to do more work. So I don't like electricity, so I've had to do more work on that, whereas see that, just straightforward maths, isn't it? Was it difficult to teach A-level? I preferred teaching A-level because it was more interesting. You had a smaller class size and everybody there wanted to do it because they chose to do it. At GCSE, I found it more difficult because there's like more people in the room. I know once we did a practical, some stuff, and we just didn't have enough stools for everybody to sit down, because I think at that point we had like 35 people in my class in my first school I worked in. So it's difficult to get everybody in the room. And even though they were clever people, a lot of them weren't doing it because they loved physics, they did it because they had to. So I preferred A-level. Although the teaching was more academic, I really quite liked that challenge. Jack says you don't like fluid dynamics. Yeah, I think that's... I think fluid dynamics, I mean, at uni, we had to do a lot of stuff where we were modelling at the time using MATLAB, and I just didn't really understand it fully. But, you know, some people like that. Right. So, yeah. Do I still teach? At the moment, no, because I'm doing this full-time. So this is my full-time job. Hopefully I can make enough money from it to keep doing what I'm doing. But I'm moving into a bigger office, and I've got a plan to make at least, I don't know, at least another 1,000 A-level physics videos over the coming years. So yeah, my plan is to basically invest all of my time and any money I've got into growing this into the biggest channel on YouTube in terms of A-level physics, and the best website, the best resources. And that just doesn't include stuff like the videos. I've got books and things as well. So if you're year 12, buy this book. If you're year 11, buy book 1 of the Daily Workout series. Okay. What was my favourite uni module? I liked solids under stress because it's very mathematical and just lots of working out problems. So yeah, definitely looking at like solids under stress and things like that, and also tribology or tribology. Basically, that's how metals kind of, or materials come into contact with one another. So if you've got like two surfaces in contact, how you kind of lubricate them to kind of reduce friction. That was something I really liked as well. Okay, can I do a collab with Sean Donnelly? I'd love to. Sean, Free Science Lessons, you're welcome at any point into my new studio. It's going to be mega. Right, so let's open some Legos. So this one over here, for those of you who've been paying attention for the last few weeks, we've been adding more Lego from the new Space series into my collection. Last night, this one over here, I did a bit more research. This is Orion, okay? And actually, if you look at Orion, he's actually holding a shield over here, and actually he's holding a club. I always thought, because I hadn't really done much work on like this kind of side of astronomy, that he was holding like a bow and arrow, but actually this is his shield, and this is his club, which is why this is Orion here. You can see the kind of star person. This is Orion's club over here, and they're holding their shield. So that is Orion. But what do we have for tonight? So tonight we have got yet another minifig box. We'll see which one we've got. It might be a repeat, it might be something new. So let's just open it. What do you reckon? Shall I open the Lego? So here we go. Okay, this is one we don't have yet. So I don't think we need. Do we need the instructions? Maybe. Right. So for this one, I think that's like a new Lego piece, isn't it? So it's got some instructions here of how to build it. let me just zoom in a bit. We will get to some proper physics in a minute. This is like a backpack that has this on each side. Okay, so it's got like one of these Technic pieces that goes in each side. This kind of plugs into it like that. And this is like an M-tron figure. They're like the baddies in like Lego space, I think. Oh, here's the head. So we've either got like a green face, or we've got, let's just use that one there, shall we? And then we've got the helmet. On the side we have a pressure gauge. I quite like that. That's nice. A nice bit of Lego there. And then he can hold. Am I doing that right? There we go. Yeah, this is the baddie in Lego, and then there's also this kind of like M-tron thing over here. So we've got a spare bit there. I'll add that to my spares box. I'm getting far too much Lego now, but at some point I can claim this on business expenses. So here's the M-tron figure. I do like the plates at the bottom with the stars on. So here we go. That's the latest figure, and that means, looking at the range, I think we've only got a couple more things to get. Right, so enough of that. Let's see what people are saying. Yeah, I do like Lego, but also it's kind of become a bit of an obsession. However, this is my job. I'm an adult. I earn quite a lot of money doing this, more than I was as a teacher, and yet I get to play with Lego, and this is like my world at the moment. Let's see what people are saying. So some people have maths paper 1 tomorrow. For all of you, Josh and other people, Josh, music and media, if you've got maths paper 1 tomorrow, I hope it all goes really well. So I know there might not be as many A-level people as normal. Obviously, I'm going to be here tonight and tomorrow and the next day, ready to kind of help you prepare for your physics paper 2. Now, the reason I can't show AQA papers is just due to copyright. So I'm going to use some OCR paper tonight. We're going to go through the multiple choice questions and basically answer this. And of course, if you want to play along at home, then do ask. Do kind of put stuff in. Am I friends with Science Shorts Guy? Not yet, but Zed Physics emailed me tonight. He's got an exciting thing that we might work on together, or I can like kind of help him get into school. So do stay tuned because there's going to be more stuff that I'm doing. Definitely with other YouTube creators, because you know, people like Bison Maths, I know a lot of you follow them. Primrose Kitten, actually, me and Jen from Primrose Kitten, we had a chat today on the phone. So yeah, I'd like to do whatever I can to work with other creators and kind of share the love that we have for teaching. So Faraday's law of electromagnetic induction basically says that the EMF is going to be proportional to the rate of change of flux. Okay, and of course, if you've got a number of turns, that would be n d phi, or a delta phi by delta t. So I think this pen is running out. I'm going to use it till it ends. So people are saying D. So the EMF induced in a circuit is directly proportional to the rate of change of magnetic flux linkage. Okay, and that's the flux linked through all the coils, and therefore the answer would be D. Okay, now you only get current if you've got a complete circuit. So what we tend to look at A level is the electromotive force, maybe across the ends of a wire, rather than the current flowing a complete circuit. And also this depends not on magnetic flux density, which is B, but on the total flux linked. So that's going to be, in this case, D. Okay, I think this pen is on its last legs. Okay, right, so let's see what people are saying. Okay, there's lots of stuff going on. Okay, so I think there's some stuff here. I'm not going to get controversial. I'd love to collaborate with Mr. Bruff. What it needs, though, is people like you emailing Mr. Bruff and other people. And I think what you need to do is just contact the other people, because I'd love to work with whoever. You know, I think although we are all trying to earn money in different ways, I'd love to collaborate with as many people as possible. And I think we all just like, want to kind of help people like you in all of your subjects. And obviously, Mr. Bruff, brilliant at English, and there's other English teachers out there on YouTube, and I'd just happily work with any of them. Okay, I don't know Mr. Everything English, but yeah, I think there's loads of other people there who are brilliant. Right, so anyway, let's not get into beef with other YouTubers. It's all joyous and lovely. So monochromatic light from a laser is incident normally on the diffraction grating. A series of bright dots are formed on a distant screen. Which two terms can be used to describe these bright dots? So, first of all, again, let's see what people say. Back to the physics, Muffy. Excellent. Is it A, B, C, or D? So the reason that, so you've got monochromatic light, diffraction grating. The reason that we have the light kind of spreading apart, so basically we have all of these dots, all of these gaps in that diffraction grating, and as the monochromatic light goes through, what we get is diffraction at each of these holes over here. So where there's a gap, the light, because it's going to be a similar wavelength to the width of that slit in the diffraction grating, we get diffraction. So it's not reflection, it's not refraction. So actually the answer must be the first one. And of course what we then have is we have points where you've got a path difference in the rays of light, and if you've got a path difference, this leads to a phase difference, and then we might have constructive and destructive interference, and that means those two aren't right. The only one which has two correct answers is A. So everybody out there, so we've got Josh, music and media, we've got EM, Minnie, Madcraft, Nabil, Ahmed, the Slow-Mo, Lambros, Scarface, Harper Irwin, yeah. Oh yeah, by the way, the Slow-Mo says, do a collab with Veritasium. I'd love to do that. Oh, hold on. That's just a blank piece of paper. Right, here we go. Number 3. The current in the lamp is 2 milliamps. PD across it is 6 volts. What's the energy transferred in the lamp over a period of 3 hours? No calculators, please. You do not need your calculator for this, I'm suspecting. Now, of course, we know that the energy transferred is equal to ITV. Okay, this is more of like a paper 1 question for AQA, but of course, if you're AQA, you've done this recently. So that's going to be equal to the current, which is 2.0 times 10 to the minus 3, times the time, which is 3.0 hours, times 60 minutes, times 60 seconds, times the potential difference of 6.0. Okay, maybe you do need your calculator. So this is OCR spec, these questions. These are from the 2021 paper, I believe. But of course, a lot of it, the later stuff is going to be suitable for anybody doing any exam board. People are saying C. Let's see what it says. So 2 times 10 to the minus 3 times 3 times 60 times 60 times 6. 129.6. And that means the answer here is D. So for a question like this, see people are retracting their answers. Do not look at the numbers. If it's a numerical multiple choice question, I would say just approach it like any other physics question. Write down the equation, put your numbers in, work out the answer, and then check and see what that's equal to. So yeah, the answer EM is D. Right, number 4. This one here, again, is suitable, I think, for Edexcel, for AQA, OCR A and B. The magnitude of the charge on each sphere is the same. The point P is on the line joining the centres of the spheres, and it's the same distance from the centre of each sphere. Which statement is correct? So you've got a positive and a negative sphere. Are they going to attract or repel? Well, they've got opposite charges, so they'd attract. So will the negatively charged particle P move to the right? No, it would want to move to the left. The direction of the electric field at P is to the left. So the electric field, if we think about drawing some field lines, they go from positive to negative. Now they're going to leave the surface at right angles to it. So we get basically something, if we were to look at the field, a bit like that. Okay, it's not a perfect diagram. So the direction of the field is to the right. So that's not true. The electric potential is 0. Yeah, so actually this one is true, because say for example that was at maybe whatever that is, say +1, that's -1. There's going to be like a gradient between them, and where that is equal to 0, the value of 0 is equal to the midpoint. So this one is true. The magnitude of the electric field strength at P is 0 is not true, because you'd have a component of the electric field strength due to that positive charge. And of course, the electric field strength is going to be equal to the charge divided by the radius squared. Okay, and that's 1 over 4 pi epsilon naught. Okay, and so you're going to basically have a positive value there, and there's also going to be added to this the strength of the field due to that, and therefore that's going to have a certain value in size. So the magnitude isn't 0, but there's going to be a magnitude of the electric field at this point. So here the answer for 4 is C. Let's see, slow-mo, Jack, Harper, Josh, Nabil, all correct answers. Well done. Okay, oh, here we go. This is nice. A circuit with 4 LEDs is shown below. 2 LEDs are lit. Which 2 LEDs are lit? So, if that's the circuit, we've got our positive end here and the negative end. So conventional current is going to go away from here. Let's just take a journey. It's going to go along here. When it gets to this junction, the conventional current is going to go in the direction of the arrow. So it's going to go this way through Q. And when it gets to this one here, it can't go that way. So it must be going this way. So the first one that's lit is Q. Okay, and of course, as it goes around here, it goes under a little bridge. It keeps going up here. And when it gets to this point here, it can't really go that way because of the potential up here. It's bigger than the potential down here. So it's going to go back down S. It's going to go to this junction here, and then it's going to go back over here and along that journey. So if we think about an electron, it would go this way around the circuit. It's going to go up through Q, back down through S, and back to here. So the only one which is correct is D. So we've got Jack, Harper, Lambros, hello Lambros, Daniel, hello Daniel, Josh, loads of people getting the right answer there. So this one over here, I think it's quite a nice question, isn't it? It'd be great fun to draw that. That looks like a really fun diagram to draw. And for the people who haven't seen the stuff I've done, I do all my own drawings, although I've got other people helping with other bits and pieces. If you've been working through my daily workout book, every picture in here is something I've somehow drawn, or the tables I've put together. So all of these pictures drawn laboriously in PowerPoint, which I think is amazing. So yeah, all of these drawn by hand. Okay, right. A student is modelling the decay of a charge of a capacitor using this equation here. So we can say delta Q is delta T equals minus 0.2 Q. They use a change in time equal to 0.5 of a second. Okay, sorry, I'm just going to sort something out over here. So we've got the charge left on the capacitor at time t. So at 0, Q is equal to 1,000. Okay, so we can basically look at the change in charge is equal to minus 0.2 Q times delta T. Okay, now of course delta T is equal to 0.5, and we're going to multiply that by 0.2 Q for delta Q. So that means delta Q is going to be equal to Q times 0.5 times 0.2, which is 0.1. Okay, and so we're just going to look at the magnitude of that. Now, if you've got 1,000, you multiply that by 0.1, you get 100, and then you take 100 away from that to get 900. So effectively what we're doing is we're taking a value of Q and we're multiplying by 0.9 to get, you know, the second value. So Q1 is equal, Q1 times 0.9 is equal to Q2, and then you just have Q2 times 0.9 is equal to Q3. So all we need to do is take this number here, 1,000 times 0.9 is 900, times 0.9 is 810, times 0.9 is equal to 729. So we're reducing by 10% each time. And it is a negative thing, but I just want to look at the size of the change, because what you do then is basically you have 900, 10% of that is 90, 10% of this would be 81, and then, you know, basically you take this number away from that number to get this number, and then you take away this number here, 810 minus 81 is equal to 79. So the value of Q in microcoulombs at time 1.5 is just going to be this value here, which is 729, which is C. Okay. Okay. Right, so people are asking, yeah, that's all it is. So Nabil, the answer is, for this one over here, I think this is like, I don't like this equation really. It's just not my favourite. But all you need to do is effectively, because we know we have this exponential decay, it's going to decay by the same proportion in the same time interval. And if we know that basically from, you've got minus 0.2 and 0.5, that's equal to 0.1, so it's a 10% decay each time. We just look at this number and multiply it by 0.9 to get that number. That makes sense? If you're not sure, leave it, move on, and then come back to it at the end. Right, number 7. Here we go, thermistor question. Again, this is OCR paper 2 stuff. AQA people, you've already done this. You never need to look at potential divider circuits again after a couple of weeks. So let's see what you think the answer is. So there's lots of information here. I would label it. The resistance of the resistor is R. The resistance of the thermistor is 2.5 R. And the PD across the thermistor is equal to 5.0 volts. Okay. Now, effectively, because we know that that's maybe R1, and we're going to call that R2, R1 over R2 is equal to V1 over V2. So the relationship between the resistances is the same as the resistance between their potential differences. Now, if that's 2.5R is 5, then all I'm going to do is 5 divided by 2.5 to say that here the potential difference across that is 2. Because the potential difference here is 2.5 times the potential difference there. And that means 2 and 5 make 7. So the total PD across both components is the same as the EMF, which in this case is B equal to 7. So 7 says Ibtisam, excellent. B says Nabil Harper Lambos. Hello everybody. Do you get an equation sheet for A-level physics, Meshraf? Yes, you do. And actually, the equations you get for A-level are better than for GCSE. They, depending on the exam board, they will give you like everything you need to know. I mean, there's a lot more equations, but you don't have to remember them. It's basically a thing of, can you just find on the data sheet which equation you might need. By the way, these are just my simple like A5 versions or A4 versions you can kind of print out. Okay, here we go. A double slit used in an interference experiment to look at two sources of light K and L. Now, if it's a double slit, then it's going to have the same grating. And that means the distance or the number of gratings per meter is going to be the same. So we've got the wavelength, the separation, distance between them. What is the separation between adjacent bright fringes for source L? So what is this value in here? We know that W is equal to lambda D over S, and S is equal to lambda D over W, which must be a constant value. So we know the wavelength here, we've got the distance to the screen, and we've got the separation between fringes. Now, let's look at K and L. We can say that lambda K times the distance K over the fringe separation of K must be equal to the wavelength of L times the distance to screen L divided by the separation of the fringes of L as well. Now, we know all of these things, but we don't know the separation of bright fringes for L. So basically, this is our unknown. And therefore, WL is equal to lambda L dL over lambda K dK multiplied by WK. So all we need to do then is kind of put these numbers in. So lambda L, so you've got 0.8 times dL, 0.5. And we're going to divide that by this times this, which is just 1. And we're going to multiply that by 1.2. Gives me an answer of 0.48. And therefore WL is 0.48, which in this case is A. So again, I haven't even looked at these numbers. I've just looked at this kind of sort of relationship between the two things. There's probably other ways you can do it, but the answer for this is A. Okay, so yeah. Is this a 6-mark question? Horan, maybe for some of you doing AQA, this is like flashbacks to paper 1. Okay, number 9. Here we go. Oh, this is nice. I like this one. Stationary or standing wave formed in a tube is shown below. So we can see we've basically got, in the length of that tube, which is L, we've basically got one wavelength here, and then we've got a quarter. So we know that the wavelength of that is going to be equal to lambda plus lambda over 4, which is 5 lambda over 4. Okay, that's just what we know. The tube is closed at one end, so we'd have a node at the end and an antinode at the open end. We've got the length of the tube and the speed of sound. What's the frequency? Well, we know V is equal to F lambda, so the frequency is equal to the wave speed divided by the wavelength. Now here we've got the length in terms of the wavelength, so the wavelength is going to be equal to 4L over 5. And of course L is equal to 3.5, so 4 times 3.5 divided by 5 is equal to 2.8, so that's equal to 340 over 2.8, which equals 121.42, which to two significant figures is B. Harper, Nabil, excellent work so far. Right. Right, there we go, that's all it is. So a question like this, we've got a nice diagram actually. You know, of course, that if you've got an open tube at one end, you have an antinode at the open end and a node at the closed end. If it was a tube open at both ends, you'd have antinodes at both ends. And if you had a wave on a string, you'd have a node at both ends. Okay, and of course, don't look at the numbers, do the calculation first and then see which number gives you the closest thing over here. And to two significant figures, because we've got two significant figures in the data, that's why it's given as 120. Okay, we've got about another 5 more questions to go. I hope everybody out there is doing all right. I know a lot of you have maths tomorrow, but to be honest, by doing maths A-level, the physics, or the maths in the physics A-level seems pretty easy. Okay, simple circuit. We've got an EMF of 6 volts. The current from the battery is 30 milliamps. Okay, so if it's 10 milliamps down there, then it must be 20 milliamps going up here. And you'd have 20 milliamps here and here. The resistors are identical, and that means, you know, Kirchhoff's second law, we've got a 6 volt EMF, which is shared between these two things. So you'd have 3.0 volts across this and 3.0 volts across that. The power dissipated is going to be equal to VI, which is just 3.0 times 20 times 10 to the minus 3, or actually that's 3.0 times 20 milliamps, so that's going to be equal to 60 milliwatts. So here I think the answer 10 is B. Okay, by the way, yeah, these are OCR questions, but a lot of the physics is going to be the same for AQA. Of course, it's not ideal for AQA. I've got some ideas about ways around that, so I'm going to try and do more stuff if you've been looking at physics and maths tutor to kind of show AQA questions. But at the moment, this is like OCR questions, but a lot of it, probably over half the content, is still useful if you're at AQA or EdXL or anybody else. Okay, yeah. Okay, we've now got 2 graphs of displacement against time for waves S and T. They meet at a point in space. There's a resultant wave. What's the frequency and amplitude? So I'm going to draw this. Basically, you've got +1 and -3, which is going to give a resultant of 2. We've got a resultant of 0 and a resultant of 3 minus 1, which is 2. So basically what we'd have is a wave that the resultant wave looks a bit like this. Okay, that's not a bad sketch, is it? So what is the amplitude? The amplitude of that wave is going to be equal to 2.0 millimeters. And of course the time period is going to be the same. So the time for one wave cycle, t, is equal to 50 milliseconds. The frequency is 1 over the time period, and that's going to be 1 divided by 50 times 10 to the minus 3, which is equal to 20 hertz. So that's the calculation. Is that right? No. 5.0. So 1 divided by 5 times 10 to the minus 3 is 200 hertz. So it can't be this, can't be that, can't be that one. So the answer is C. Easy. Yeah. There we go. Should I do another collab with Tom Rocks Maths? I think I should. That's probably one of my most successful videos. Great guy. I'd love to do more stuff like that. Yeah. Nabil, I'll contact him after this and see if we can do some videos together. Right, number 12. Oh, it's just endless, isn't it? This kind of physics revision. But we're good. We're good. Exam QA. I don't know that person. To be honest, a lot of the stuff in the chat I can remember at the time, but I'm not really writing down. So if you think there's people I should collaborate with, send them a message saying they should collaborate with me. I'd love to do that. And of course, also send me an email at hello. I'm just going to write it down here. I do read all of my emails, and I do try and respond if I can. But if you email hello@physicsonline.com, then you can always send me suggestions, and I'll kind of probably have that more in my mind after the live stream is finished. So exam QA, again, I'd love to do more stuff with them. So we've got a coil here. We know the angle theta is equal to 30 degrees. What's the magnetic flux linkage? So the magnetic flux linkage is going to be equal to BAN cos 30. Okay, so we've got the magnetic flux density times the area times the number of turns on that coil times cos 30 for the angle that it's making. We can say that's equal to the magnetic flux density, 0.050, times the area. They've given it to us in meters squared, luckily, times 200 turns, times cos 30. Isn't cos 30 just a half? Oh no, it's not, it's point that. So 0.05 times 1.2 times 10 to the minus 4 times 200 times cos 30 is equal to 1.04 times 10 to the minus 3, which happens to be that one over there. So the answer must be D. So don't look at these, don't get distracted, do the maths properly, do the physics, and then look at the answer and see which one that equates to. So D, yeah. Yeah, cos 30 can sometimes get confused with sine 30. To be honest, I forget what's what because I'm not doing maths all the time like you guys are. So I've completely forgotten what's equal to a half or 1 over root 2. Basically, trust your calculator. That's what it's for. And yeah, don't make the mistakes of trying to like do a shorthand. Type all the numbers into your calculator. Make sure it's in degrees or radians, and that will give you the correct answer 100% of the time. So yeah, that's from the normal to the field lines. Yes, that's right, yeah. Okay, thorium-232 emits 2 alpha particles. So I'm going to write this out. So you've got thorium-232, and it emits 2 alpha particles. So that's 4-2 alpha plus 4-2 alpha, and 2 beta minus. So beta minus plus beta minus. Now that's got no nucleons, and effectively the charge on it is -1. So plus we have our unknown new thing. So we've had 232 things in the middle. We've got rid of 4 and 4 nucleons. So we're going to take away 8 to get 224 as the number at the top, A. Now the number at the bottom, we've got 90. We've lost 2 protons, lost another 2 protons, but then we've had a neutron turn to a proton and a neutron turn to a proton. So effectively we've had 90 take away 2, because you've got 2 minus 1 and minus 1, which is all 0, and that's equal to 88, and that's the number of protons left. So it's 224 and 88, which happens to be A. So the answer for 13 is A. Can I post more community posts testing on some magnetic fields and nuclear? I'll try and do that, yeah. Somebody says that dark energy is the most vague topic. That's because nobody knows what it is, and the teachers are like, yeah, there's this thing, it's like called dark energy, it does stuff, but we know it causes the expansion of the universe, but we don't know what it is. So yeah, that's what it is. It's just a vague topic. It's often the last thing written about in the specification. Okay, right, this question is OCR-A only. It's a medical physics one. Okay, so this one here, if you're AQA, EdXL, don't panic. You've got loads of time, but basically we've got the density and the speed, and we want to look at the percentage of the intensity reflected at the boundary. Now for this, what you need to do is, because I cannot remember this, is you need to look in your data book, and basically we can see that IR over I naught is equal to Z2 minus Z1 squared over Z2 plus Z1 squared. Okay, so AQA people, don't panic. OCR people, you don't need to remember it, you just need to know where to find it in your data book or whatever formula sheet you're using. So Z is just going to be equal to rho C. So it's basically this number times this number. So F is just going to be rho of 1 times C type, which is 1. And you've got 1.2 times 1.5, which is 1.8. So that's basically our Z numbers. And because we're dividing one by the other, the units don't matter. So we've got Z2, so you've got 1.8 minus 1 squared, divided by 1.8 plus 1 squared. So that's going to be equal to 0.8 squared, divided by 2.8 squared, which is 0.08. So that's a proportion of reflected to incident intensity of sound, which is 0.08, which is 8%. And so the answer here is going to be B. Is that right? I think that's right. I'm not an examiner for AQA or OCR. I'm completely neutral. However, I do know people at both exam boards. I've had some lovely chats with people recently from OCR. I've actually run some training courses on behalf of EdXL for teachers. So I've been like a Pearson kind of instructor person. So I've done that for EdXL, but I'm still completely independent of what I do. Okay, the last one. Everybody can have a go at this. If you're watching this, doesn't matter which exam board you're doing, here's some data about a beta source. Now, all of that is irrelevant. You don't need to know any of this. How do you describe the data shown? You've got basically slightly different values for the activity or the count rate for all of these sources. How do you describe it? Is this an exponential set of data? No, it's not. Is it linear? No linear pattern there. Is it random or spontaneous? So I would say that this is random data. Now, although the emission of particles is a random and spontaneous thing, we can't really affect how it's emitted. The actual data that we receive is random. So here the answer is C. Okay. Right. So I would say, looking at the chat, there's some really good questions there. Do you need to know calculus for physics? You do not need to be able to integrate or differentiate in physics if you are doing OCR. I believe there's a tiny little bit when it comes to looking at, I think maybe EdXL, they kind of expect a little bit more, but basically all of you doing maths, you've done differentiation integration at that level. The stuff for physics A level is like down here, and it's basically, it's good to know about. I would say everybody who's got a physics degree or an engineering degree has done lots of differentiation and integration at university, and I think it's really important to understand why they're important, but you don't have to know it in the exams. But if your teachers are using that to help explain things, I think that's a really, really good thing. Yeah. Now, Mashraf says you've got a friend who wants to do A-level physics but not A-level maths. Are they going to be extremely disadvantaged? It depends. I mean, a couple of years ago, I had a boy in my tutor group who was, he didn't do A-level maths, but he was predicted like an A star in physics and also an A star in chemistry and A star in biology because he just loved sciences. He didn't have enough time to do the A-level maths as well, but it didn't disadvantage him at all because you can basically learn all the maths you need for A-level physics. If you want to do something with it afterwards, say you want to go and do like a degree that might need maths as well as physics, I think it's important to do. It depends on what your other choices are. And if there's the option to do AS physics as like a fourth A-level choice, that's a really good idea because it gives you at least a bit more of an understanding than what you've done at GCSE. Biology, chem and physics is a strange combination for A-levels. Maybe, but he likes science, and that's what he wanted and stuff. So yeah, I think it's all good. Right, which would I say the hardest exam board is? Does it matter? I don't think, for a lot of people asking this, it matters, because ultimately, if there's a lot of them follow pretty much the same specification. Last year, AQA had a harder paper one. This year, OCRA had a harder paper. I don't think it really matters. And ultimately, if you're a good student working hard, you're going to get a good grade whichever exam board you do. If there was an exam board that was easier than everybody else, then every school would go and do that, because that would be the most sensible thing to do for their students. The fact that there's a whole range of exam boards taken, if it's EduCAS, OCRA, OCRB, AQA and EdXL, the fact there's so many of them tells you that one isn't easier than the others, otherwise everybody would be doing that. Yeah. Any last minute tips for the multiple choice paper? Yeah, I would say multiple choice. If you're not sure about the approach to any question, skip it, move on, do something else and come back to it later, and look at the total time so you've got plenty of time for the longer wordy answers that come up in the paper. Right, that is it for tonight. I'll be back again tomorrow. I'm going to be doing some OCR questions in a similar vein to how I did it tonight. And of course, I'm going to be doing probably a double super session on Wednesday night before your exams on Thursday. But of course, hopefully all of you are doing all right, and I will finish it there. Thank you very much.